So we are talking about a simple concept today, which is, so we will continue talking about first law of thermodynamics, but in that context, we need to talk about what does it mean to be in equilibrium, a concept which is often the same as change being reversible. So these concepts are simple, but they start to confuse. So let's take just a moment to make sure what we're talking about. And I will be drawing a little bit. Mostly I will be waving my hands vigorously to show you what's going on. So if you're just looking at the notes on the video later, it might all make sense to you, but then the ones you are attending do get a benefit, right? So let's say you have one side of a container at temperature T1 and the other side of the container at temperature T2, okay? And this is something through which heat can pass back and forth. Or you could also imagine that it is one side of the container at P1 pressure and the other side at P2 pressure, and the container can act, and the boundary can actually move to the left and right. In either of these cases, oh, the color inversion is gone. That's correct. So if T1 is equal to T2, then on an average, no heat will be moving from left to right, right? Now, if I make T1 slightly larger than T2, then which direction will heat go? From T1 to T2 or T2 to T1? T1 to T2, right? So if I make T1 slightly larger than T2, heat goes from 1, so container 1, to 2. At the same time, not at the same time, in opposite, if I made T1 slightly smaller than T2, then heat goes from 2 to 1, right? So the point being that as you change the direction, as you change the driving force, as you make small changes in the temperature, the direction of heat flow responds immediately, and it starts moving in the opposite direction until equilibrium is attained, right? Until as much heat flows that T1 becomes T2. So this might seem to you like, duh, this is what should happen, right? What's the big deal? Now let's think about a different case where we had T1 and T2, but T2 was much more than T1. In this case, heat is, if you're coming late, you can just leave your homework at any point over here, now or before the class. Just make sure to do it before the class. In this case, if T2 is much more than T1, heat is going from right to left, right? Now I change it. I decrease T2. Decrease, my writing is terrible here. Decrease T2 a little. If you decrease T2 a little, what will happen to the direction of heat change? It won't change, right? Heat will still go in because you decreased it just a little bit. So the change in the driving force, the change in the temperature did not cause the heat flow direction to change. You can imagine the same thing with pressure, right? If pressure 2 was much more than pressure 1, and you just decrease P2, P2 is decreased slightly. This is a bit easier to imagine by looking at a container. Let's say I have this container over here and there is some gas and I have a piston. This thing is just put at a higher pressure, right? So I have really made it very, very tight. So if it's so tight that the thing is not basically, it's compressed over here, right? Now I make it slightly looser. If I make it slightly looser, does it mean that the direction of the piston move changed? No, it is still tight. It's not doing anything. Now you could imagine a container where it is very loosely kept and everything is at equilibrium. And in this case, if you decrease the pressure from top, then the movement will start happening in one direction, right? And if you increase the pressure on top, the movement will start happening in another direction. So reversible change is when, let me write it down. Carefully. So the point is that if the system is at equilibrium, if P1 is equal to T2, or if P1 is equal to P2, then any change in the system by changing P1 slightly more than P2 will be reversible, or by making P1 slightly smaller than P2, or making temperature slightly larger than T2, or making T1 slightly smaller than T2. So systems at equilibrium undergo reversible change. And the other thing also applies, the opposite direction. If you are changing a system reversibly, it stays under equilibrium. Also, so the opposite is also true. If change is happening reversibly, system stays in equilibrium, right? So why does this matter? The reason this matters a lot is because if a system is not in equilibrium, we cannot use equation of state. We become clueless regarding how to describe the system. Systems in equilibrium follow equation of state, right? If a system is not in equilibrium, it will not follow an equation of state. Equation of state is a direct consequence of equilibrium, right? Equation of state happened because we said in order to describe any system, we need 4 variables. A relation exists under equilibrium. If there is equilibrium, the 4 variables are connected to each other through, and this looks like a U, but it's a V. So for example, P is equal to P of NVT, or T is equal to T of NVP. We can use such a relation. The simplest one is the ideal gas law. We also saw virial equation. We saw van der Waals equation. So such equations are going to help us if the system is in equilibrium. So what we want to do now is to really use this concept of reversible change, which allows us to enforce equilibrium, to calculate the work done during expansion, okay? So that's, I said a bunch, let's see what it means. So let's calculate reversible change and work done. So let's imagine a gas which is undergoing, this is pressure on the y-axis and volume on the left axis. Let's imagine a perfect gas for now, okay? The gas is perfect. So if it was in equilibrium, it would follow PV is equal to nRT. Let me ask you a question. If a perfect gas, let's say all of you are particles comprising a perfect gas, right? And half of you are in this corner, or let's say half of you on that corner. You really don't like me, right? So half of you go, all of you, actually not just half of you, all of you go sit in that corner. Are you in equilibrium then? Why not? Yeah, exactly. And our interparticle distance is very small. Under equilibrium, everything should be moving, randomly colliding with each other. So we cannot say PV is equal to nRT for that one. Clearly, pressure is not even uniform. You have a bunch of pressure in that corner. In this corner, there is no pressure, right? So a perfect gas might or might not be in equilibrium. If a perfect gas is in equilibrium, then you can use PV is equal to nRT. A van der Waals gas might or might not be in equilibrium. If it is in equilibrium, you can use the corresponding equation of state. But anytime a system is out of equilibrium, life becomes very, very hard. The sad thing about thermodynamics is almost everything is out of equilibrium. Biological systems especially are completely out of equilibrium. You think of a protein or a kinase or a DNA or an RNA, it's not under equilibrium. Always there is some non-equilibrium existing in the body. And non-equilibrium is very hard to study. That said, there are ways to deal with how systems get to equilibrium, to study systems when they're slightly far from equilibrium. So in a certain sense, equilibrium thermodynamics is a notion that never even exists in reality. We have to wait till the end of the universe for equilibrium to happen. Yet it is very powerful, okay? So it's good to study this with just a tiny bit of skepticism, knowing that it is never always true, yet it happens to be very powerful. So let's consider a perfect gas expanding from volume VI to VF. So let's say this is VI, and let's say this is VF. And let's say that at the final volume, its pressure becomes PF, some PF over here. So this is the final point of the gas, PF, comma VF, or VF, comma PF. But let's write down VF, comma PF. That's consistent. So VF, comma PF. So the question is, my first question for you is, what should have been the initial pressure of the gas? Assuming everything is perfect and reversible, what can we say about PI? Should it be more than PF or smaller than PF? Why? Well, I didn't tell you the change is isothermal. So what you are saying is justified if it's a constant temperature process, correct? You're absolutely correct. At constant T. If I allow temperature also to change, then it won't be true, right? Then you have to think more carefully. So you're absolutely correct. If temperature is constant, number of gas moles is constant, R is of course a constant, then pressure and volume are inversely related. So this means that you must have started from some pressure PI. So if you underwent reversible change, or if the gas underwent reversible change, then we know this equation is going to be true. And how does this equation look like if you plot it in this? And in the math module, I have some equation. This is why, this is again one of those situations where it's so easy to whip out your calculator and try to start to plot things, but it's so much better if you can think through it without opening a calculator. You have to plot the equation xy is equal to constant. Xy is equal to constant looks something like this. Or PV is equal to nRT when temperature is constant looks something like this. So that is the equation of PV is equal to nRT. You can see that as volume goes to 0, pressure goes to infinity, right? And as pressure goes to 0, volume goes to infinity. And it's, I think this is the equation of a hyperbola, if I'm not wrong. So this is the equation for PV is equal to nRT. Now let's calculate the work done. Case 1. So we want to calculate the work done during expansion. And our convention is work done on the system, right? We are not thinking about work done by the system. We'll stay consistent with this convention. Work done during expansion on system. What's the formula? The formula is delta W is equal to minus P external dV. Now, if the process is reversible, then what can we say about minus P external? It will be always equal to the pressure of the gas. We can use equation of state. So this case, P external will be the same as minus P gas dV. And since it's reversible, it's under equilibrium. Here we can use minus nRT by V dV. So we can calculate the net work done on the system is equal to integral of delta W is equal to minus VI to VF nRT by V dV. All of this is constant, remember, because it's an isothermal process. Again, if it was not isothermal and you will be doing many problems like that, life becomes complicated. You will be looking at adiabatic processes, isobaric processes, temperature won't be constant. I posted some Khan Academy videos, which is quite nicely done, where he calculates lots of pressure volume curves and everything. I recommend watching it. It will give you some intuition. So this becomes minus nRT ln VF by VI, right? After integrating it. Does this make sense? We know that VF is more than VI. Therefore, ln, so let's do a sanity check. We know VF is more than VI, therefore ln VF by, no. Sorry about that. Oh, yeah. Good. Therefore, ln VF by VI is going to be positive. Therefore, W is going to be negative. Makes sense, right? So this thing is positive. This thing is more than 1. Therefore, ln, sorry. Therefore, ln of this thing is positive, right? If VF by VI is more than 1, then ln of Vf by Vi is positive, right? Because ln of x is positive if x is more than 1. So this means that W is negative. Does that make sense relative to what we said last time? It does, right? When you expanded a gas, negative work was done on the system. What does it mean? It means system had to do work against its surrounding in order to expand, right? If the gas was expanding, you would be able to get some work out of it. So in general, when a system expands, which could be your muscles expanding or the steam in the steam engine expanding, that's when you get work out of it. So this makes sense. Work done on system is negative. Work done by system is positive. Okay, so this was case 1. I'm going to draw this plot again on the next page because we are going to, and also write down the equation. So we had pressure volume. And we went to some PF from some PI. This was volume VI. This was volume VF. And we got W is equal to, first of all, W is equal to minus integral dW. What did I write there? Delta W is equal to minus nRT ln VF by VI. And this is the same as minus PdV. And we could use, the key thing here was that for reversible change, we could use P is equal to P external. It's because it was reversible change. This equation that we wrote down has a geometrical meaning on the figure that I drew under the left, which goes back to really the basic definition of an integral. How do we define an integral in calculus, Calc 1? Go ahead.
The
Area under the curve. So which area, which curve is it in this plot? This dashed one or this solid one? Solid one. So it is this area that we just calculated, right? So the work that we can get out of a gas by expanding it is equal to the work shown here is equal to area shown by shaded red lines. Now let's get to case 2, which is expansion is irreversible. So in this first case, physically what you did was you started at a pressure which was large and you very, very slowly reduce the pressure, right? You reduce the pressure and you were like, are you okay? You want to relax? It's like me teaching you thermodynamics over the course of next 10 years. Every time I teach a concept, I make sure you understand it over the next 2 months, and that would be completely reversible, right? Unfortunately, it doesn't happen that way. Unfortunately, it feels like boom, 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 concept after concept after concept. So it can be irreversible. Go ahead.
Will the area of the curve always be work done by the system?
Good point. So the work done on the system is minus multiplied by area under the curve, right? So you're absolutely correct. So the better way to think about it is what I said. Work done on the system is always minus times area under the curve. And you're correct. In general, the work done by the system would be area under the curve to get rid of the minus sign. So this is very slow process. So reversible change is also very, very slow, right? You're giving system time to adjust. At any point under this curve, so you're basically very, very slowly and gradually, it's also called a quasi-static change. This is also a term you will see. Quasi-static means that it's almost static, but not quite, right? It's very, very slowly changing. So at any point, if you decrease the pressure in one direction, the system would start moving back in that direction. So you had decreased the pressure and the system was expanding. But at some point you stop and you start increasing the pressure again, the system will again start contracting. Irreversible change is not like that. Irreversible changes when you say, bam, all of a sudden I'm decreasing the pressure to PF. It's like me coming in the first class and telling you, this is all of PChem 1. Tomorrow we have an exam. That's not going to be a good situation, right? You will be unhappy out of it. In that case, we can write down the work done as W is equal to, once again, minus integral of delta W, once again, which is the same as P external dV, but now P external is not equal to P. The gas is unhappy. You just bombarded it with a lot of, you just suddenly, in this case, you decrease the pressure all of a sudden to PF. The integral, however, is easy because in this case, the PF is simply, the P external is simply PF. It is the final pressure of the gas. It is a constant. So the integral is even easier. You don't have to do anything. It's just a constant number as you go from VI to VF. So this becomes minus PF, VF minus VI. So in this curve over here, the shaded red area was the work done during reversible change. How do we look at this area? How do we plot it in the curve above? Go ahead. It's the rectangle, right? It is this PF. PF is equal to this height, and VF minus VI is equal to this thing. So we can plot it in another color. Is equal to shaded green region, and let's call this figure 1 in figure 1. Is this W positive or negative? What do you think? I'm sorry, I don't know your name. You know his name? No, to your right. What's your name?
Oh, Max.
Max, Max, what do you think? Is this positive or negative? Negative, right? Because VF is more than VI and PF is positive and it's a negative number. So let's think about the work. So once again, work done on system is negative. But now let's think about in both cases. So case reversible and case irreversible. And I want you to think about the work done by system, okay, which is just this thing with a minus sign. So in this case, reversible change, it is plus nRT ln VF by VI. And then a piece of advice that I can give you is, it's good if something is positive when it comes to work done, when you're calculating expressions, don't omit the plus sign. Like in this case, I could have just omitted the plus sign. Just to be careful, it's a good idea to write down the plus sign. I won't be cutting marks if you don't write the plus sign, but you're less likely to make mistakes if you explicitly account that is positive. You will remember what's going on. And while the second one is going to be plus PF, VF minus VI. Which one is larger? Which case is the work done by the system larger? The red shaded area or the green shaded area? Red, right? Looking at this is one of those things where the geometry makes it very easy. If I asked you to ignore this curve and just look at this equation, it's kind of hard to say, right? Why is the top one more than the bottom one? You have, your math definitely has to be better than my math. I can't say just by looking at it. It's not obvious to me at all. But if I do a bit of geometry and look at that curve, then it's super obvious what's going on. And that's a really profound observation, that the maximum work that can be done by a system is during reversible change. This is super, super important. This is really one of, this is our first glimpse of the second law of thermodynamics. the more you are doing change irreversibly, the less work you will be able to get out of a system. So, and this is almost like a philosophical statement. If you want to be very, very productive, if you want to be very, very efficient, it's best to stay in equilibrium. It's best not to stay out of equilibrium. Sometimes it feels we do 50 things very, very quickly and we will have lots of productivity. It doesn't happen that way, right? So it's almost philosophical. Here we showed it mathematically for a gas undergoing expansion during an isothermal process, that this one is larger and this one is smaller. Mathematically also, it's not hard to prove. You will have to just jiggle a little bit, but from the curves, it's really obvious. So here I showed for an isothermal expansion, but it's true in general. And why is it true in general? In order to see that, we will have to go to second law of thermodynamics. Entropy is the thing that comes into picture to quantify the difference between reversible and irreversible change. Any questions about this? Go ahead. Which one? This thing or? Oh no, good point. That's a plus. The next negative is correct. Yeah. So is this. Good catch. Sorry about that. Any other questions? So this is what did we do right now? We calculated the work done during isothermal expansion of a gas. You could also calculate the work done during isothermal compression of a gas, right? You have the same thing. And you could think about it, how would it apply during reversible or irreversible change? You would see that, yeah, you can go and think about that, but it's the same idea. Any questions before I move to the next thing? Okay. So let's think about first law of thermodynamics again. It says change in internal energy is a state function. Internal energy is a state function, and the change in it can be written as an exact differential. This is the same as heat given to the system, which depends on the path, work done on the system, which depends on the path. And you just saw the path dependence, right? In both cases, the work was totally different. The beautiful thing is the internal energy change of the system will be the same for both paths. And that's really, really awesome. The work we have seen so far is a very specific type of work. It's what we call expansion work, right? It's specifically volume expansion. That's not the only type of work a system can undergo. There can be other type of works which we can call as delta W, others. And let's take a moment to think about what the other type of work can be. Most of the time, almost all the time in this semester, we will be thinking about expansion work, except when we get to multi-component system. Then we will be talking about chemical work. For now, it's just going to be expansion work. So let's think about type of work and the corresponding delta W that we have. So we just saw for expansion work, what is the value of delta W? The expression starts with a minus. Minus P external. Who said that? Great, good job, because you said P external. Don't say PdV, right? That's like a recipe for making mistakes. It's never PdV. I'm not asking about reversible expansion. I'm talking, so that's, I was waiting for that. Good job. So I mean, I have a sad story about missing out on this P external versus P. So in India, when I was in high school, everyone has to take this engineering school entrance exam. Some of you might have heard about it. It's called an IIT, and you have to take this exam, which is very, very hard. So I had prepared very well. I went to take it. And there was a problem where I had to calculate work done. And I forgot that it is P external and not P. And I lost 3 points. And those 3 points meant that I could not study chemistry. I got material science. which was turned out to be quite good. It was awesome. When I eventually, I'm a chemistry professor now, but those 3 marks, because I forgot P external and P, there are actually 2 problems I forgot. One was, the other one was the name of a catalyst, which I still remember, but I forgot that day. That's another story. So let's talk about another type of work, which is surface expansion. So here we were talking about really volume expansion, but we can also think about a film, right? And you are stretching the film in different directions. You are increasing the area. In that case, what would be the work done? Any ideas? So pressure says something about volume. What is the similar quantity about area? I gave you a hint, thin film. Surface tension, right? It will be surface tension minus gamma surface tension. It's the typical, and you same, again, it should be external. And what should be multiplied by now? It should be multiplied by the area, right? Change in area of the system. So if you have a 2D system, if you're making some complicated graphene molecule sheet or something like that, then you have to think about gamma external multiplied by dA. So this is volume expansion. This is surface expansion. What is the natural third type of expansion we can think of? Go ahead. Extension, right? Just linear extension. Or let's just call it extension. In this case, we will have 4 tension and change in length, right? So you can see all of them have the same dimension. All of them have the dimension of, what's the dimension of delta W? Any ideas? All right. Huh? Energy, right? Joule or Newton's time meter. It's kilocalorie or something. We saw it in last class when we did the iron chloride test. So, and you can see in every case, the dimension is always that of energy or Newton meter or joule or kcal or cal or electron volt, whatever you want to see, but it's basically energy. We can think about more work. This is all mechanical work. We can think about electrical work. Electrical work will be given by some electric potential. What should we multiply by here? Change in what? This is a tough one. I heard something. Change in charge. That's correct. dq. Okay. So we are not going to be worrying about these things. You will rarely be seeing them in the course of this semester, but it's important to be aware, especially when you read a research paper or things like that, you might see things. And all of these go into these delta W others. We can also go in the type of work I do. I always think about information work, not always, every once in a while, where the change is happening in knowledge multiplied by some driving force. So I'm doing work on you right now. It's not mechanical work, even though Marco tries to occasionally drag me up to the other floor. That would be mechanical, but it's mostly, you know, something is changing, right? It's not exactly reversible. The change of information is not in the other direction. Once in a while, I learn something from you, but mostly it's in one direction, right? So it can get very abstract. In fact, you can make it very, very abstract by thinking about some force multiplied by change in some variable chi. And these two things are called conjugate variables. And this is some generalized force. So you can make it as abstract as possible, but we are not going to worry about this. But just to give you a flavor, there are different types of work that can be treated in the first law of thermodynamics. Most of what we are interested in can be captured just by looking at the pressure volume expansion work. So when a problem tells you to calculate the work done, typically it should specify that you are being asked about expansion work. If not, you are well justified to ask, are we asking about expansion work or not? But if nothing is specified, then you should be careful. Is there a reason for you to believe that there might be other types of work going on? So think carefully before just jumping into PDV. There might be other types of work happening. Any questions? Okay, so we spoke a little bit about internal energy last time, right? We said that internal energy for an ideal gas is equal to 3n/2 RT, right? Ideal gas, point particles. We said it is equal to DOF RT/2. And you might be at this point, why did you write R? Why did you not write KB? So that purely depends on whether you are looking at number of moles or number of molecules, right? If you're looking at number of particles or molecules, then you do KB. But if you're looking at number of moles, then you do R. This is ideal gas made of molecules. For non-ideal gases, it is going to be different. So we saw a little bit of internal energy. We saw a little bit of work done, right? How to calculate the work done. The thing we haven't thought about yet is the heat, how to really calculate the change of heat of a system, which turns out is the simplest thing to measure in an experiment, right? Because we all have probably, even though I'm a theoretical scientist, I have still used calorimeters during my undergrad, right? You have bomb calorimeters and all those other calorimeters, and you can measure the heat change in a system. So heat is actually the simplest way to probe a system. Let's talk about that a little bit. So the way to measure heat in a system, how do we measure heat in a typical experiment? Anyone remembers? What's the thing that we normally measure? Huh? Change in temperature? But I was looking for something specific. That's correct, you do measure change in temperature, but change in temperature is one part of the picture. There is another part of the picture. Q is equal to? What is C? Heat capacity. Heat capacity is the thing that we really worry about, right? And heat capacity is also given in tables. Heat capacity turns out to be one of the most informative things in thermodynamics. If you can measure the heat capacity of a material or of a chemical as a function of temperature, turns out you can go and calculate every single thing about it, assuming equilibrium, not out of equilibrium. So what is this heat capacity? Heat capacity C, as the name says, is the capacity for heat. C measures. So you said the change in temperature, right? But what I'm saying is, in order to change the temperature by a certain amount, different materials will need, different chemicals will need different amounts of heat, right? And heat capacity is that ratio. How much heat do you need to give to a system to change its temperature by 1 unit of temperature? She said specific heat capacity, that is 1 unit per temperature for 1 mole of a substance or 1 gram of a substance, right? Because otherwise, if you have 1 gram of a substance and you need 50 kilojoule and you have 100 gram of a substance, you're going to need 50 multiplied by 100 kilojoule, right? So heat capacity, but I am right now not talking about specific heat. I'm talking about heat capacity, measures the ratio of heat Q absorbed by a system. This ratio with respect, so it's the ratio of the heat absorbed by a system to the amount of temperature change. In other words, C is equal to delta Q by delta T. This is the intuitive definition. Let's be a bit more rigorous about it. By the way, I want to see how many students are in class. As I keep forgetting. I will just do a quick head count. Wow, it's like 60. I'm honored. You made my day. There is a movie on Netflix called The Chair. Have any of you seen it? It's a TV show. It's very funny. It's got a very old professor who is always grumbling, why does no one come to my class? You should watch it, it's really funny. So rigorously, this thing is, but today's homework submission day. I'll measure the next day. I should not get too happy. So heat capacity can be measured in two ways. Most of the times when we measure it in a furnace, what is unique about a furnace? Its volume cannot change, right? The pressure inside a furnace can keep building up and up and up. And if you're not careful, the whole thing might break. That's why making a good furnace is very, very hard. It has to be able to withdraw a lot of, it has to be able to withstand a lot of pressure. So heat capacity can be measured under constant. First case is it can be measured under constant volume, in which case it is written as C subscript V. I wrote it as a small v, you could write it as a capital V, it doesn't really matter. And this is defined most rigorously as change in delta Q divided by change in temperature at constant V. Let's use our first law of thermodynamics here now. First law of thermodynamics says that du is equal to delta Q plus delta W. And let's ignore other types of work, okay? From now on, even though I mentioned the other types of work, I want you to just remember they exist, but in the math, we are not going to use this. Let's say that there is only one type of work, which is minus P external dV, pressure volume work. If it's a constant volume process, what can we say about dV? 0. So what can we say about du? Equal to delta Q. And that's really awesome. We just showed that du is equal to delta Q under constant volume. This means that heat capacity at constant volume, which looks ugly, it's like a squiggly delta in the numerator and then another squiggly delta in the denominator, which is hard to calculate. And Q is a path function. You have to know how exactly did you drive the system, is equal to partial U by partial T at constant. Oh, it's annoying. So at constant V, this is path dependent, is equal to partial U by partial T at constant V. This is state dependent. And that's super powerful because we don't have to worry about what path did this system take. We can directly work with the internal energy, which is a much well-behaved state function, and we can use rules of calculus to do these derivatives. Go ahead.
What the dt looks like non-partial derivative and the other one looks like partial?
dt is always partial. But the thing is, temperature is the change that you're observing. So the temperature is a the dt in the denominator is a well-defined number. You know, you're thinking about a small change. The question is, in order to have the small change, how much did the numerator change by? And this one, you have to really worry about how did you change the system, whether you went from here to here, or whether you went just straight. While this one is a state function, and it's wonderful. Let me write it down on the next page. And then we will stop there. And I want you to think about only one thing, and we will talk about CP the next time, the heat capacity constant pressure. So I just said that this is equal to partial U by partial T at constant volume. So what is U for ideal gas of point particles? It is 3n by 2 RT, right? So what is partial U by partial T at constant V for an ideal gas? Is 3nR by 2. This is a constant, right? Does it depend on temperature? No. Does it depend on volume? No. Of point particles. If you had some molecules, it would still be 3R by 2 multiplied by some function of n. And I posted something in Slack where it shows you how to get these numbers for other molecules. In the next homework, you can refer to that cheat sheet to calculate it for different molecules, and it gives you the reason for why it is done that way. But the point is that for an ideal gas made up of point particles or molecules, the heat capacity at constant volume is a constant independent of temperature. So if I plot it in a curve, CV versus temperature, how is it going to look? Straight line. This is what people thought until 1903 or something. And this was totally wrong. If you measure the heat capacity of a chemical, in reality, it looks at very high temperature, it does become constant. But at low temperature, it goes to zero. And this is the first time in order to explain, and in fact, at low temperature, it goes to zero as the cube of temperature. And the only person to explain this was a very, very famous scientist with lots and lots of hair, Einstein. It took Einstein to explain this in 1905. He was able to mix quantum mechanics with this concept of statistical mechanics, and then he was able to show why heat capacity goes to zero. So we won't be talking about why this behavior happens, but we will talk about heat capacity a lot in the coming couple of lectures. So you can go and read it as to why Einstein was able to show that. And next time we will talk about heat capacity in more detail. Actually, Einstein did